today we're going to be covering the Merton model, which is a classic model for the default of a firm, developed in the 70s by Robert Merton. And it should come as no surprise that because it was developed in the 70s, we are going to see Black-Scholes-Merton technology in this model. So essentially, this takes the option pricing framework that Black-Scholes and Merton developed in the 70s and uses it as a tool for default modeling. So, the basic setup, we have a firm. So that's all we're going to be concerned with is just one particular firm. The firm will issue one zero coupon bond with value BT. So think of today as time little t. That bond matures at time capital T, and it has a face value of B dollars. So the way we can think of that is if we draw our timeline, and so we're standing here at time t, the value of this bond is BT, and the bond pays B dollars back at time t. Being a zero coupon bond means there are no coupons in between now and maturity. It's only the face value of B dollars that's paid back at maturity. And when you think about a firm, this is one of the ways that a firm raises capital. Really, a bond is of course just a fancy word for a loan. So when a company issues a bond here at time t, we can think of it as the bondholder is loaning the firm BT dollars and will get back B dollars when the loan matures. And that is going to be the crux of default. Basically, these bondholders, because this is a loan, the firm needs to be paying them back at maturity T. Then we also have the equity of the firm, and we're going to denote that by ST, as is done in most presentations of the Black-Scholes model. Think of it like the stock price. That is the value of the firm to the shareholders. So if you own stock in the firm, this is, in this example, the total value of the firm's equity. Then the total value of the firm, we will write as VT, so that's the equity in the firm plus all the borrowed capital. So think of it as you take the value of the stocks plus the value of all the money that has been borrowed through this loan. And we're working over this finite time horizon because in terms of default, what we really care about is that time cap T. So that's the basic framework, that's the basic structure. Now we start to think about default. Again, as we mentioned in the previous slide, default occurs if the firm misses its payment to the bondholders at time capital T. So in this framework, in this model, default can only happen at time capital T. If we look back here, the only liability that the firm faces is this need to pay the bondholders their money, their face value, B, at maturity. So default happens if for some reason that payment cannot be made by the firm. So this is just recalling that value equation from the previous slide. And we have two cases. Either the firm has enough money to pay the bondholders, or it doesn't. Case one will be the case where the firm does have enough money to pay the bondholders. So the value of the firm at the maturity of the bond is bigger than the face value of the bond. So the value of the firm is sufficient to make that payment to bondholders. So bondholders receive the payment of B dollars. The shareholders get the leftovers. So looking at this equation here, if we solve for S, you see that S is equal to V minus B. So this is the equity in the firm after the bondholders have been paid back. And so this is the case of no default. So this is the case when everything is fine, business is proceeding as usual. The other case is the case where, of course, the firm does default. So case two, liabilities exceed assets So the amount that needs to be paid to the bondholders is bigger than or equal to the value of the firm. So this is the case where the firm does in fact default. And in that case, the shareholder equity goes to zero. So you want to think of this as the firm going out of business. The firm is bankrupt, the firm is done. So the stock price goes to zero. And this is what we call a limited liability option being exercised on the part of the shareholders. So this is fairly intuitive with people's understanding of the stock market. If you own a stock and for some reason that company goes out of business and that company has outstanding debt that it cannot pay, as a stockholder, you don't get someone knocking on your door saying your stock is now worth zero, but we need your house and your car to help pay these debts. That doesn't happen with equity ownership. The equity owners have this limited liability option. The equity goes to zero, and then basically the bondholders take what's left. So of course, this is a less than or equal to. If it's actually equal to, then the bondholders just take all the value. They get made whole. They get their full face value B paid. But there's no value left over, and so the firm is liquidated. The firm is gone. In the case where the value of the firm is strictly less than B, the way to think of it is that the bondholders liquidate the firm and claim the proceeds from that. So a simple way to think of it is the bondholders liquidate the building, the desks, the computers, any assets that the firm has, turn that into cash, and then take the value of that as a partial payment at time t. So mechanically, that's how things work. But we can now take these two cases and write them as payoffs. If we want to start thinking in terms of the Black-Scholes framework, we want to think payoffs because we want to start thinking about bringing option math into this. Here we had something that happened to the shareholders and something that happened to the bondholders. This was case 2. In case 1, we also had something happening to the shareholders and something happening to the bondholders. So in each case, each of these parties has a deterministic payoff, and say for the shareholders, you have 2 possibilities. For the bondholders, we have 2 possibilities. So what does this look like in default? First, let's address the shareholder. Well, remember, if the company is able to make its payment, so remember, no default was the case where VT was bigger than B. So if there is no default, then VT minus B, the equity left over after the company made its payment to bondholders, this is what the equity was worth. This was capital ST. In the case when the company did in fact default, the equity went to zero. And so that was this limited liability protection to the equity holders, protection from this case being something negative. So essentially this means the shareholders are getting whatever is bigger. This value minus so VT minus B, if it's greater than or equal to 0, and if that's negative, we take 0. So that should remind you exactly of the payoff of a call option. So this is the payoff of a European call option with underlying V sub T, strike price B, and maturity T. So that's one way now we can see options are brought into the mix here. For the bondholders, well, the bondholders either get their money back, they get their face value, which is going to be money with interest, or in the case of default, they get the value of the firm. So if the value of the firm is big enough to make the bond payment, they get B. If it's not, then they get the value of the firm. So they get whichever is smaller. Hence we have the bondholder payoff at time cap t is the smaller of these two. We can then rewrite that in this way, and this is something that you can quickly check. You can just check that in each case this right-hand side here is actually equal to the minimum of the two. So think of it this way. If B minus VT is positive, then that's the bigger. So that's the result of this maximum. And that, of course, would be the case if B minus VT is positive. That's the case of a default where the bond payment, the face value of the bond is more than the value of the firm. So if that's the bigger of the two, that's the default case. So the maximum would pick up B minus VT. So we would get B minus minus VT. So this would be VT if we default. And then the other case is when the maximum is 0. So that's the case where VT is in fact bigger than V. So the case of no default. So in that case, when there's no default, this is 0, and this is just B. So we see that this, in fact, does sync up. This right-hand side does, in fact, sync up with this minimum version of the payoff. But looking at this, we now notice that this maximum is the payoff of a European put option with strike price B, maturity cap T, and again, underlying asset V sub T. So what we're seeing here now is that we have our shareholder payoff written as the payoff of a call option, a European call option, and then we have the bondholder payoff written as a function of a European put option. It's B, this constant B, minus the value of that put option. So this means that we can use technology from the Black-Scholes model to say something about the default of the firm. So we're going to have to remember our Black-Scholes model for an option price. And so recall that we actually need the cumulative distribution function for a standard normal random variable. If you have a standard normal random variable, this is its cumulative distribution function, which, remember, by definition, would be the probability that your random variable is less than or equal to this value x. Graphically, if we think of our standard normal density, then this CDF represents the area under the curve from minus infinity up to x. Okay, so remember the key here. The shareholders have a call option. Bondholders have their payoff being something that depends on a put option. Okay, so first let's focus on the bondholders. And note that we're going to go back into the Black-Scholes world and assume that the value of the firm is a geometric Brownian motion. And remember, there are two ways we can depict that. So this is one way we depict the geometric Brownian motion. And so you can think of this on the left as your net return over some very small interval of time. And we have a deterministic piece of return coming from this drift mu. And then we have this random piece of return. And remember that this is coming from a normally distributed random variable reflected here. This is the other version. So this is the stochastic differential equation that represents geometric Brownian motion. And then this is the solution to that. And WT is a standard Brownian motion in that solution. Okay, and so this is something that, of course, we use Ito's formula to get from this SDE to its solution here. Now, coming back to the equity holder's payoff, remember, it was the payoff of a call option. And in Black-Scholes theory, we can get the time little t, so that's the earlier time price of the option. We have an analytic formula, so we're using CBS for call option price under the Black-Scholes model. It's a function of both time and value of the underlying. So the underlying is the value of the firm V. And then we have our parameters. We have our fixed continuously compounded rate of interest. Sigma is the underlying asset's volatility. And then we have B, which in our case here is the strike price of the option, and T the maturity. And the analytic formula for that call option price is given here on the right. So this n is, as mentioned on the previous slide, the cumulative distribution function for a standard normal random variable. And we're feeding the CDF and these DT1 and DT2 values, which are given down here. So it is a complicated formula, but remember, the point is that it is an analytic formula. So we have this analytic formula for the value of the equity holders, the value of the stock, 4 times before maturity in this case. Now we can also talk about the bondholder value. So the bond value at maturity was given by this payoff that we looked at on a previous slide. Well, since this maximum is the payoff of a put, we again use the fact that we have an analytic formula for the put option price. So put option price in the Black-Scholes model at time t, value of the firm Vt with the same parameters as the previous option. Other term here is a deterministic value of B. So this is B dollars, but we need to discount it back to time t. So remember, we're standing here at time t. And if we have B dollars at time capital T, that needs to be brought back over that time period from little t to big T. So we're discounting over the amount of time passing between little t and big T. So present value of B dollars at time little t minus the Black-Scholes value for the put option. And if we simplify this, we go back and here again is another result from the Black-Scholes model. This is the formula for the Black-Scholes price of the put option. You notice we use the same DT1 and DT2. When you simplify, we get to equation 7 here, which is now the value of the bond. So in this framework, we now have a deterministic value for the bond, as well as a deterministic value for the equity of the firm. Okay, so we haven't really used this in terms of something like prediction of default or something we can say about default. That will be next. But up until this point, we can use this structure of this bond to come up with the arbitrage-free value for the equity of the firm and the arbitrage-free value for the debt or the bond of the firm at time little t prior to maturity of the bond. We can also think about probability of default. Come back to our assumptions of the Black-Scholes model. So we know under the risk-neutral measure, if we take the log of the value of the firm, because it's a geometric Brownian motion, then we have a normally distributed random variable. Now let's just look back at that geometric Brownian motion equation for a second. So this is the value of the firm in this model. If you take the natural log of this, the natural log splits this product into a sum. So you'll get natural log of V naught. That's just some constant. Then the natural log of this exponential, remember the natural log and the exponential are inverse functions. So those will go away. And so natural log of Vt will be a constant plus what's in the exponent here, which is a deterministic piece, and then a constant times a normal. So the result will be, in fact, normally distributed. And so this is our mean. Here's that constant that pops out. Here's what was in that exponent. This is the mean of that. So that random variable has this mean and this variance. Well, if we know the distribution of the value of the firm, and of course, remember, default happens if the firm can't pay its bills. So if the firm's value isn't enough to pay the bondholders, we have a default. So the probability that the firm actually defaults at time cap t is the probability of this default condition. And we can work through that. So now, because the natural log is a strictly increasing function, we can take logs of both sides of this inequality. We don't change the event at all. So this default probability will be the probability of log of the value of the firm at time cap t is less than or equal to log of b. And then we can actually plug in what we usually call a z-score. So this natural log of vt, we know its distribution. We know it's normal. Here's the mean. So we take natural log of vt, we subtract that mean, and this is the variance, sigma squared cap t, so we divide by the variance. So we do a z-score here, and then we make the same change to natural log of b. So we subtract that mean, and we divide by the standard deviation. So by doing so, by z-scoring this here will be a standard normal. So by subtracting its mean and dividing by its standard deviation, we've transformed it into a standard normal random variable, which means the probability that this standard normal random variable is less than or equal to this constant. This may be complicated, but it's just a constant. That's obtained by taking this constant and plugging it in to the cumulative distribution function for the standard normal, which is what we had written as n. So this gives us a way to obtain the risk-neutral probability of default. So in this model, you can then back out a default probability using this framework. Now, of course, you have to keep in mind there are limitations here. The Black-Scholes model is built on this assumption that the value is log normal. So the assumption of normality is in here. And so when you're doing things like modeling default probabilities, the normal distribution can be a little bit dangerous because it lacks kurtosis, it lacks weight in its tails, and tends to dramatically underestimate the probability of extreme events. But nonetheless, this gives us a very straightforward, natural, classical model for modeling default probabilities.